Okay, we are on 6.3, describing chemical bonding. And I'm going to go ahead and skip the warm-up and jump down to an introduction to chemical bonding. When we have two atoms approaching each other, each of them has their own electron cloud, and as those electron clouds begin to approach each other, you're going to get repulsive forces between those electron clouds because they're both negatively charged. And then you also have nucleus from each atom approaching each other, and the positive charges in the nucleus are also going to be repelling each other, and so this repulsion kind of slows down the approaching atoms, and it converts kinetic energy to potential energy. And each nucleus attracts the approaching atom's electron cloud, and you get sort of this overlap of clouds between the adjacent nuclei, and that is when your chemical bond forms between them. And we have three different types of chemical bonds. The first one is an ionic bond, which is between a metal and a nonmetal. The second is a covalent, that's between two nonmetals. Third is a metallic, which is between two metals. If you take a look at the next page, we're going to start by talking about ionic bonds in detail. So let me explain what's happening here. Generally speaking, you're going to have large metal atoms from groups 1 and 2 on the left side of the periodic table, combining with smaller non-metal atoms from the far side of the right side of the periodic table from groups 16 and 17. Let's use sodium and chlorine as an example. When sodium and chlorine start to approach each other, their electron clouds are going to be repelling each other, and that kind of slows the atoms down as they approach. But also the adjacent nuclei, since they're both positively charged, are going to be attracted to the negatively charged electron cloud on the neighboring atom. And this positively charged nucleus would be attracted to the neighboring electron cloud on the approaching atom. And what happens is chlorine is a much smaller atom than sodium, which means the valence electrons in the sodium atom will actually be closer to the positively charged nucleus in chlorine than in its own atom. So what does that mean? Well, it's going to cause that valence electron to get so close that chlorine actually kind of snatches it. We say that it's sort of like transferred over to chlorine. So you could think of this as sort of like a tug of war between electrons, and the nonmetal, which has a smaller atomic radius, is going to win. So in ionic bonds, they generally say that the metal transfers its valence electrons to the nonmetal because the valence electrons in the metal are so close to the nonmetal. Okay. Now, what happens when this electron leaves? Well, you're going to get a positively charged sodium atom. So this would be an Na with a +1 charge, revealing the 8 valence electrons it had beneath that 1 electron in the outermost shell. And then the chloride ion is going to form a -1 charge because it acquired that 1 electron. And now this is totally content because it has an octet in its outermost shell. Now, if we're talking specifically about the structure of an ionic compound that contains ionic bonds, you're going to have a very distinct organization of cations and anions in a 3-dimensional array. It's a solid known as a crystal lattice. And if you take a look at the next page, this is a crystal lattice, and since the cations and the anions are right next to each other, there's going to be a lot of interactions between them, which makes those interactions strong, which means you're going to have really high melting temperatures for ionic compounds. Okay? Now, down here, we've got a summary of the ionic bonding concept that we just talked about. Remember, think about ionic bond formation as extremely unequal electron sharing. The metal and the nonmetal nuclei attract the valence electrons between them. The nonmetal pulls those electrons closer to its own nucleus, so it captures the metal's valence electron, and it forms a metal ion and a nonmetal anion. All of these points are summarized here. Ionic compounds form between metals and nonmetals whose difference in electronegativity exceed 1.7. So this delta En means difference in electronegativity. you have to know that the difference in electronegativity has to exceed 1.7 in order for it to be ionic. Metal atoms are going to transfer one or more of their valence electrons to the more electronegative non-metal atoms. And then ionic compounds form crystal lattices, and that's why we have really high melting points, because there are so many attractive forces between the cations and the anions in the lattice. And then fourth, the formulas of ionic compounds represent the smallest whole number ratios of cations to anions that are electrically neutral. If we go to the next page, take a look at the quick check. What event occurs when atoms of metals and nonmetals react to become cations and anions? Well, metals lose their valence electrons to nonmetals. And that is how a metal becomes a cation and a nonmetal becomes an anion. Number two, what are the three types of chemical bonds based on the different elements involved? Well, we have an ionic bond, which is between a metal and a nonmetal. We have a covalent bond, which is between two nonmetals. And then we have a metallic bond, which is between two metals. Number three, which chemical families in the periodic table are typically associated with ionic bond formation? Well, this would be metals from groups 1 or 2 combining with nonmetals from groups 16 or 17. Let's take a look at the practice problems here. Number 1 says, write formulas for the ionic compounds formed when the following elements combine. So remember, here we're crossing charges. Barium has a +2, bromine has a -1. You get BaBr2. Here, beryllium has a +2, oxygen is a -2, they cancel, you get BeO. Here, strontium is a +2, nitrogen is a -3, you get Sr3N2. Over here on the right, Mg has a +2, chlorine is a -1, you get MgCl2. Here, francium is +1, fluorine is -1, they cancel, you get FrF. Now down here, they want us to justify that these bonds are actually ionic by looking at the difference in electronegativities. For this, you have to turn back to the electronegativity table that is in section 6.2. You should have earmarked that page. If you look at RB, RB has a value of 0.8. Fluorine has a value of 4.0. All you have to do is subtract those two values so that you get a positive difference. And in this case, you're going to end up getting 3.2, and that is within the ionic bond range. Okay. For the next one, if you're looking at RA is 0.9, chlorine is 3.0. So 3 minus 0.9 is going to end up giving you a difference of 2.1, and this is ionic. Okay. If you're looking at the next one, you've got K and Br. K is 0.8, Br is 2.8. Subtract those two, and you're going to end up getting a difference of 2.0. That's within the ionic bond range. For the last one, sodium is 0.9, oxygen is 3.5. 3.5 minus 0.9 is going to be 2.6, which is also ionic. Number 3, write formulas for the ionic compounds formed when the following elements combine. Use the difference in electronegativity values. Arrange the compounds in order of the increasing ionic character of the bonds in each compound. Okay, so again, we're crossing charges here to get the chemical formula. We've been doing this for a while, so I'm just going to go ahead and write all the chemical formulas down. And then after this, what we're going to do is we're going to take a look at the table at the electronegativity values and subtract them. This difference in electronegativity is 2.1. This is 1.8. LICL is 2.0. CSF is 3.3. RB2O is 2.7. Now, this is the highest, and this is the lowest. So if we're putting these in order of increasing ionic character, you would want to start with the lowest one first. So it would be SRBR2 as the lowest, followed by LICL at 2.0, followed by Na3N at 2.1, RB2O at 2.7, and CSF at 3.3, okay? Let's turn to the next page and let's talk about covalent bonds. The difference between covalent bonds and ionic bonds is that ionic bonding was basically a transfer or capturing of a valence electron by a nonmetal from a metal. Covalent bonding, since this is between two nonmetals, this is going to involve sharing of electrons. And the question is going to be, is it equal sharing or is it unequal sharing? So anytime you've got a bond between two atoms of the same nonmetal, it's going to be a covalent bond. And we could use hydrogen as an example, which would be H2. How does a bond form in this case? Well, what happens is the two hydrogen atoms are going to approach each other, and their kinetic energy increases as the electron clouds are going to be attracted to the approaching positive nucleus in the other atom. And the two atoms keep moving together until the repulsive forces between those electron clouds and the two positively charged nuclei approaching slow them down, and their kinetic energy gets converted into potential energy. And eventually, these electron clouds between the two atoms are going to overlap, and they're going to overlap enough to cause attractive forces to exceed the repulsive forces, because the negatively charged electrons are going to be attracted to the neighboring positive charge on the other nucleus. So the two atoms are going to settle into this position next to each other with the pair of valence electrons in a cloud of negative charge between the two nuclei. And as the electron clouds overlap, the two valence electrons are going to experience the most attractive force between the two adjacent nuclei. And this force of attraction of the pair of electrons between the adjacent nuclei is your single covalent bond. So we are sharing one pair of electrons in a single covalent bond. And since these are the same atoms, they're both hydrogen, they have the same electronegativity values, so they're going to share that pair of electrons equally, okay? The electronegativity difference associated with the atoms in a bond have to be 0. So the bonded electrons are going to spend most of their time equidistant between the two hydrogen nuclei, and that means that the electron charge cloud is going to be the greatest halfway between them. And that's going to be true whenever you've got the same atoms bonded to each other. They're going to equally share the valence electrons, and this is sometimes referred to as a pure covalent or nonpolar covalent bond. They will often abbreviate this as just a nonpolar bond. And it is assumed that you know that it's covalent, okay? Now, if you take a look down here, this is a summary of covalent bonding. Covalent bonds typically form between two nonmetal atoms. Because there is no electron transferring occurring and no ions forming, everything before and after the bond forms is going to stay electrically neutral. The force of attraction in a covalent bond is between a pair of electrons and the two adjacent positive nuclei. It's not between a cation and an anion. Electrons in covalent bonds are always associated in pairs. This means if you have a single bond, it's going to be one pair of electrons. So I have something like this. This would be a single bond between two hydrogens, or you can have a pair of electrons like that representing a single bond. Covalent compounds often exist as independent molecules, rather than large crystal structures, okay? Now, if we go to the next page, we're going to get more in depth in talking about covalent bonds. They're a little more complicated than ionic bonds. Table on the left-hand side of this page is something that you absolutely have to know. Now, let me tell you why. If you don't know the ranges for the differences in electronegativity and which pertains to nonpolar, polar, and ionic bonds, you will not be able to predict things like molecular polarity and bond polarity. So make sure you know this. Yes, these ranges differ depending upon the textbook, your teacher, the online resource that you're looking at. But for this class, I want you to follow this. They've given you a summary and the reading of what these differences in electronegativity mean. For instance, if the difference in electronegativity is less than 0.4, that means the bonding electrons between the two atoms spend no more of their time near one nucleus than the other. And such bonds are considered mostly covalent because the difference in electronegativity is pretty insignificant. Also, if you have a difference in electronegativity beyond 0.4, the pair of bonding electrons is going to be drawn closer to the nucleus of the atom with the higher electronegativity. That means you're going to have an unequal distribution of electrons, and that's going to result in a pole. You'll have a negative end and a positive end within a bond. So let me show you what that looks like. This bond dipole exists in polar covalent bonds. So here I've got hydrogen and chlorine bonded to each other. Chlorine is more electronegative, so it draws the electrons to itself within the bond. So you could think of it as having like a cloud of electron charge more towards the chlorine. So since we have more negative charge on that end, you can represent using Greek deltas, these are lowercase Greek deltas, the partial charges that exist within the bond. This is a partial negative on the more electronegative element and a partial positive on the less electronegative element. We can also use an arrow facing in the direction of the highest electron density or the negative end of the bond dipole. So here you see this arrow pointing in the direction of chlorine because it's more electronegative, and put a little cross on the other end, okay? Okay, now, these polar covalent bonds have an unequal sharing of electrons, and that's why we use these lowercase Greek deltas and this arrow to represent that. Now, what do we do when we have atoms that form more than one bond? Well, sometimes nonmetals need more than one electron to be stable and to have 8 electrons in their outermost shell. So I'll show you on the next page what I'm talking about there. But just so you know, if I have a single bond is going to be using a pair of electrons, and it's the weakest of the bonds. A double bond would use a pair of electrons, two pairs, and that would be stronger than a single bond. And then if you've got a triple bond is going to use 3 pairs of electrons. And triple bonds are the strongest of those 3 types of bonds, single, double, or triple. And they're also the shortest, and the single bonds are the longest. Now, how do I predict, if I'm writing a chemical formula between nonmetals, how many atoms are going to be needed? Well, let me explain. Here, let me give you carbon as an example of something that is in this group number. Carbon has 4 valence electrons. It needs 4 more to be stable. So since you could think of it as there are 4 locations where it could pair up with another electron, that's why it's going to form 4 bonds, or it tends to form 4 bonds for stability. If I'm talking about something that is in group 15, like nitrogen. Nitrogen has 5, 1, 2, 3, 4, 5, I think I do too many, 5 valence electrons. It needs 3 more. It has 3 locations where it could pair up. with something else, making 3 more bonds. Over here in group 16, oxygen as an example, I have 1, 2, 3, 4, 5, 6 valence electrons. Oxygen has 2 locations where it could pair up with another electron, and it would form 2 bonds, which it tends to do, and that makes it stable. In group 17, the halogens, fluorine is an example. Fluorine has got 7 valence electrons. It has 1 location where it could pair up with 1 more electron, and it could create a single bond. And that's why they tend to create just 1 bond, and that's what makes them stable. So there's a little trick that this textbook uses to sort of help you write out the formula between nonmetals and predict how many you would need so that they would be stable. In this case, if we're talking about phosphorus and chlorine, phosphorus is in group 15, and it has 5 valence electrons, so it needs 3 more. So if you put the number that it needs to be stable in the upper right-hand corner, and then chlorine is in group 17, it has 7 valence electrons, it needs 1 more to be stable. So I'm going to put the one that it needs here. You always put the element with the lower electronegativity here first. You're going to cross the numbers that you wrote down. That gives you PCl3. So that's the appropriate formula. It shows you how many of each you would need in order to have the proper number of valence electrons and for that to be a stable molecule, okay? Now, if you take a look at the practice problems on the next page, right here, this says, consider the difference in electronegativity values and pair up the elements aluminum, chlorine, nitrogen, and sodium to write the formula for the types of compounds identified below and justify it by using an appropriate difference in electronegativity value. If I want to write a compound with an ionic bond, I've got to have an electronegativity difference that falls within a certain range. And if you turn back to the previous page, that electronegativity difference, the electronegativity difference is greater than 1.7. So what I'm going to do is I'm going to bring together sodium, because it's in group 1, and chlorine, which is in group 17. That gives me NaCl. Its difference in electronegativity would be 2.1, which satisfies the need. Here I want a polar covalent bond. If you turn back to the previous page, polar covalent falls between 0.4 and 1.7. If I take aluminum and nitrogen and pull them together and I subtract their electronegativity values, I get 1.5. Falls within the range that I need. Non-polar covalent bond, if you look at the previous page, it needs to be a difference in electronegativity of 0. If I bring together nitrogen and chlorine, nitrogen needs 3 more electrons, chlorine needs 1. So if I cross these, I get NCl3. And the difference in electronegativity between nitrogen and chlorine is 0. Now, some people might think, well, why didn't you cross the numbers that you need here? Well, these are ionic compounds, and we use charges, right, to get the formulas for those ionic compounds. Number 2, calculate the difference in electronegativity values for the bonds in the following compounds. Then arrange them in order from those containing bonds with the electrons that are shared most equally to those in which the electrons are shared most unequally. All right. The difference in electronegativity between hydrogen and oxygen is 1.4. Here it is 0.9. Here it is 0. Here it is 1.7. Here it is 1.5. So that means for the Cl4 between the chlorines, this is shared the most equally. And then this is the highest difference. So these would be shared the most unequally. Okay. Number 3. For this table, you can fill it out and then you can scan the QR code down here to get the right answers. I'm just going to go ahead and do the first row for you. If you bring together carbon and sulfur, carbon and sulfur together are going to be CS2, and their difference in electronegativity value is going to be 0. And the nature of those bonds is going to be covalent, pure covalent or nonpolar covalent, right? The atom with the greater electron density would be neither, because if you look back at the electronegativity values for them, carbon is 2.5 and sulfur is 2.5. So neither one of these is actually going to share anything greater. And if you're wondering how I got that formula, you need 4 more electrons to make carbon happy, and sulfur has 6, so it needs 2. So if you simplify these into 1 and 2, that's how I get the CS2 when I cross them over, okay? All right, now, last thing. The strength of ionic versus covalent bonds. You might think that covalent compounds, since they contain covalent bonds and they're between nonmetals, you might think that they have the weakest bonds, especially in comparison to ionic. But what I want to show you is that on the next page, we've got quartz here. This is a quartz crystal, and it has something called network covalent bonds. And when we study compounds that have network covalent bonds, we actually see that the individual molecules in a quartz crystal are held together by covalent bonds that extend throughout the entire sample. This is nearly identical to how ionic solids have all of those attractive forces between cations and anions. Now, when you melt a network covalent solid, you have to break all of those covalent bonds within the huge molecule. And for quartz, its melting point is 1,550 degrees Celsius. This melting point reflects the strength of the bonds in this compound, which means covalent bonds can be just as strong as ionic.